These are some videos of a plane landing in a crosswind. I want you to notice the direction the plane is going, figure out what direction the wind is going, and notice where the plane ends up. Notice where the plane is pointed, notice where the runway is. Think about which way the wind must have been blowing. Here's another one. This is a little scary because the runway is right next to some water, it looks like. Look at how far it's having to angle over to get where it needs to go. This one you can actually see the plane blowing. It's a smaller plane. You can see the plane just being totally blown over onto the runway. Those videos are introducing our next problem. So I want to define a few terms. A plane's airspeed is its speed in still air. So for example, let me just show with some other vectors. So let's say we have a plane that's going 200 miles an hour in this direction. That would be its airspeed. Let's say there is a wind that is blowing 50 miles an hour. It's blowing in the same direction of the plane. So if we think about putting that wind right behind the plane, we see then that the wind is going to blow the plane faster than it's going. Its ground speed will actually be 250 miles an hour. The ground speed is the speed that it is going in relationship to the ground. So 200 of those miles per hour is actually from the plane's engine driving the plane. The other 50 miles per hour is from the wind pushing the plane, but the effect is that the plane is going 250 miles an hour with respect to the ground. Now, what if we turn that vector around and we said now it's going the opposite direction, 50 miles per hour, then that is called a headwind, and now the plane is slowed down. It's only going 150 miles an hour. But most of the time, and the ones we saw in the video, the wind is actually blowing at an angle to the plane like this. So when the wind blows, it has the effect of pushing the plane sideways and moving it to a different angle. And so you are noticing here, for example, if we have this wind blowing the plane this way, okay, the plane ends up actually having to point itself this way to compensate. So the plane, that's what was happening with the wind. The wind was blowing the plane to the left. The plane was having to angle itself to the right in order to stay straight on the runway. So the plane was compensating for the wind in these videos. So we're just going to look at what happens to the speed of a plane and its direction when a certain wind is blowing on it. So here we have a plane whose airspeed is 400 miles per hour. So that's how fast it would be going if there was no wind. There is a wind blowing at an angle of 42 degrees to the plane's path. That is, this is the jet stream, that is going at 150 miles per hour. So what would be the effect on the plane? What would be the plane's ground speed? In other words, the sum of the wind, the effect of the wind and the airspeed. So we're going to add these two vectors, and then by how many degrees must the pilot change the plane's bearing to stay on its original course? Okay, so it's going to have to point a different direction to stay on course. So remember that if we want to add two vectors, we have to move the vectors. So I'm going to just move this one over here. And I know you can't do that. You'd love to be able to do that. So this is the 150 miles per hour here. And then I'm going to take the plane, draw a vector for it, move it over here, and create the parallelogram like we did in one of the problems on a previous video. So the actual ground speed of the plane is going to be in this direction here. So I want to find what is the length of the resultant vector, and I also want to know the angle that it's going to have to correct itself. Okay, so right now it's being blown this direction. It's going to have to correct how many degrees? So what is theta going to have to be to get back on its original course? So recall that with a parallelogram, if this angle is 42, this angle up here is 180 minus 42, so that makes this angle 138, which means this angle is also 138. So I really can use either one of these triangles to do the problem. Since I'm looking for this, and also if this is theta, then because this is a parallelogram, this is also the same theta. So it really doesn't matter which triangle I use to find r and to find theta. So in part A, we're going to use the law of cosines because we have a side angle side situation. So r squared is equal to 150 squared plus 400 squared minus 2 times 150 times 400 times cosine of 138. And just to recall, remember 138 is the angle opposite side r, so that's why I know that r goes over here. Putting that in the calculator and solving for r, I end up with r is equal to 521.227 miles per hour. Then for part B, I could do either law of sines or law of cosines because I know all three sides now. However, I am very confident that this is not going to be an obtuse angle because the only obtuse angle in the triangle is 138. This is going to be an acute angle. So I'm going to use law of sines to find this angle. You can use either one. It doesn't matter. But I'm just going to show you that if I know it's acute, it's okay to use law of sines. So I'm going to say sine of theta over 150. Notice I'm putting the sine in the numerator since I'm solving for the angle. This makes the computation easier. And then I have to find another pair of angles. So if this, the only other angle I know is 138 and I know r. So I'm going to say this is sine of 138 degrees divided by r, which is 521.227. Okay. And I'm just going to show you something nifty on the calculator in just a second. So sine of theta, multiplying both sides of the equation by 150, I get 150 sine of 138 divided by 521.227. Then to find theta, many of you will compute this and then you'll say, wait a second, that seems too small for theta. That's because you haven't found sine of theta. You haven't found theta yet. You found sine of theta. So make sure to take that extra step and do the inverse sine of all of this. Now you could find the number first and then do inverse sine, but you know, I like to just do it all in one step and not do so many steps on my calculator. That's kind of a personal preference of mine, so it's kind of up to you how you do that. I have just found that students who do multiple steps tend to forget where they are in the problem and sometimes kind of get lost with their solution. So here's theta. So just to show you what I was going to do with this, this is not absolutely necessary to do in this problem, but I just wanted to show you, since we're doing lots of multi-step problems with messy numbers, here's something you can do. I know this is a value I'm going to have to use later in the problem, and so I'm going to just store it. So I'm going to go Control Store, so it picks up the answer from the previous problem, and R, and I'm going to store this value to R. So now when I get to the second part of the problem, where I'm typing in inverse sine of 150 sine of 138 over this number, so I'm going to go here, inverse sine of 150 sine of 138, and then over here divided by R. And I'll push enter. Okay, so this gives me the answer because it actually puts this R value right here. Now I could have also just copied this number here, which would have been just fine, but I just wanted to show you that as an example of what you can do. So I'm going to go ahead and put this over here so we can see it while we're talking about the problem if we need to. So you'll have this kind of available to look at. So theta is equal to 11.1 degrees. So when this plane is coming in for a landing, it's going to have to angle itself away from the wind at an angle of 11.1 degrees, so it's to get back on its course. So if it were approaching the runway, and let's say that was the direction of the runway, it would actually have to aim farther to the right because the wind's going to blow it 11.1 degrees off course, so it's going to have to aim itself 11.1 degrees in the other direction to stay on course.